In this lecture, we're going to talk about the determinants of 3 by 3 matrices. We're given a system of linear equations with 3 variables, and we have to be able to solve that using Cramer's rule. So let's dive in. Solving a system of linear equations means that you have to find out the variables like x, y, and z. This is a 3-variable system of linear equations. You find out the x value, y value, and z value. So let's see how to find out the x value in this case. In the denominator, we take the determinant of all the x, y, and z coefficients. So these are the x coefficients 1, 2, minus 5, and these are the y coefficients we have and the z coefficients. So this column is for x coefficients, this column is for y coefficients, and this column is for z coefficients. So whatever x, y, and z coefficients we have, which are on the left-hand side of the equation, you write down all of these coefficients and take the determinant of that. That's the denominator determinant. Now, the numerator determinant is calculated slightly differently. So whenever you're looking for x, you replace the x column with these constant values. So these constant values are -3, 4, -1. So you just write down these constant values, -3, 4, and -1. You replace the x coefficients with these constant values. So in place of x coefficients that we have written previously at the denominator, in place of those, you write down these constant values. But the y coefficients, which are this or this, and the z coefficients, as it appears at the bottom, or you can get it from here, y and z coefficients are the same. So whenever you're looking for x, you make sure that you replace the x coefficients with these constant values, and then you just take the determinant of that. So that's how you find out x. Similarly, you find out y, you write down the x, y, z coefficients as it appears in the previous case, or you can get it from here. The denominator determinant every time will remain the same, but the numerator determinant will change. So in this case, we're looking for y. So when you're looking for y, you replace the y coefficients with the constant terms from these equations. So as I marked over here, this is the y column, x column, y column, and z column. These are the coefficient values as it appears at the denominator. But in the case of y, this is not the coefficient values. These are the values that appears on the right-hand side of the equation, which are the constant values. So -3, 4, -1. And then you just take the determinant of that. That's how you can calculate y. And then in the case of z, the denominator determinant would remain the same. So this determinant is same. The numerator determinant, in the case of numerator determinant, the last column, which is the z column, this will be replaced by the constant values, and the x and y column would only be the coefficients of x and y as it appears at the bottom. So the only difference in each of these cases is whenever you're looking for x, you replace the x column with these constant terms. Whenever we're looking for y, you replace the y column with the constant terms, and for z, you replace the z column with the constant terms. Everything else will remain the same. This is the setup for Cramer's rule. So we just applied Cramer's rule, but we haven't really solved the system of linear equations yet. So how would you solve it? We just have to calculate the determinants. And let's try to calculate these determinants. For x, y, and z, all the denominator determinant is the same. So if we calculate for one of the cases, and then we see that if the denominator determinant is non-zero, then we'll be able to find out the unique solution for this system of linear equation. So let's go ahead. At first, the very first thing we'd like to do is we want to calculate the denominator determinant. So this is the denominator determinant I've written, and this is same for all these 3 cases of x, y, and z. So let's just calculate the denominator determinant. This is a 3 by 3 case because the system of linear equations that we are given, it has 3 variables. So the way to solve it is you pick the first element of the first row. We're working on this first element of the first row, and you ignore the entire row and ignore the entire column. So what you're left with is these values, -5, 3, 2, 3. So you take the determinant of -5, 3, 2, 3. And since we picked 1, so we've written down 1. Now, in the next case, what you do is you write down a negative sign. So this is the negative sign. This negative sign is coming from the formula. At first, positive. For the second term is negative, and then third term is positive. So that's the way it works. So I can sort of indicate it over here, positive and negative and then positive. Okay, fine. Now you select the second element of the first row and then you completely ignore that row and completely ignore the associated column. What you're now left with is 2, 3, minus 5 and 3. So you have 2, 3, minus 5 and 3. Take the determinant of that. Since we picked negative 2, we have negative 2 up front, and this negative is coming from the formula. So in the third case, what you want to do is you pick the third entry of the first row, and then you ignore the entire row and you ignore the column associated with that. So what you left is 2 minus 5 minus 5, 2. 2 minus 5 minus 5, 2. You take the determinant of that, and since we picked 5, we have to write according to this plus. So plus 5, and this is the setup. This is how you can calculate the determinant of a 3 by 3 case. Now that we have written all of these down, the way to solve a 2 by 2 determinant, we already learned in one of the previous lectures, is that you multiply the down diagonal entries minus the multiplication of the up diagonal entries. So that's how you can calculate the determinant of a 2 by 2 case. And then this negative 2 and 2 becomes plus, so it's 2, and then the determinant of that. So basically the same procedure, product of the down diagonal elements minus the product of the up diagonal elements, that results this. So in each of these cases you calculate and then multiply and sum all of them up, and this is what you get. So this is not 0. So this was the determinant, the denominator determinant. All of these denominators are the same, and we figured that the denominator determinant is not 0. It's non-zero, which is good, so we can find a unique solution. Now we can go ahead and try to calculate all the numerator determinants. So at first we calculate the numerator determinant for x and then y and then for z. So let's go ahead and try to calculate them. So this is the numerator determinant of x. The idea of calculating the determinant of a 3 by 3 case remains the same, and this idea is called the minor expansion, plus minus plus. So you pick the first element, you work on the first row, you pick this element, you write negative 3, you pick this element, but you have a minus from the formula, so negative minus 2, negative times minus 2, and then you have 5. So whenever you're selecting one of the elements from the first row, you completely ignore that row and that column, and you take a determinant of rest of the entries. So that's how you can calculate for each of these cases. Likewise, for the numerator determinant of y, you do exactly the same thing. You write down 1 minus this minus 3, and then plus this 5. You completely ignore the row and column for the element you have selected, and then you take the determinant for the rest of the entries, and then you calculate and find a certain value. The numerator determinant for z is, we can calculate the numerator determinant of z in the same way. Now that we have calculated all of these determinants that we have 4 distinct determinants here, and we have calculated all of them. Now if we plug in the value we have found from the numerator determinant and denominator determinant for x, then we can solve for x. Likewise for y and z. So let's just plug in all these values that we have found over here by calculation. So we can just plug in for x, numerator determinant of x divided by the denominator determinant of x. That results negative 9 over 7. So we just solve for x. Likewise, we can plug in the values of the denominator and the numerator for y and z, and we can solve for x, y, and z, all of them. That's how we can solve for x, y, and z, which means we just solve this system of linear equations that we were given to begin with. See you in the next lecture.